Problem 35, page 358. Here we have a wooden block of mass m resting on a frictionless horizontal surface is attached to a rod of length L and a end of negligible mass. A bullet of mass m traveling parallel to the horizontal surface and perpendicular to the road with a speed v hits the block and becomes embedded in it. After the collision, the bullet will stay inside the wooden block box. It means we have an inelastic or perfect inelastic collision. Part A, what is the angular momentum of the bullet block system? I have to find L of the system. We have a system of box, we can say of block and bullet. So you know the summation of tau external equals to dl divided by dt. You know this is an application to the conservation of angular momentum. What we have here as external F, we have the weight, we have the reaction here, and we have the tension is internal, it's not external. We don't need to put the tension. So here we have only N and mg. You know here the axis here is like this. Anyway, N and mg don't have a contribution to the moment of force. First of all, because N is parallel to the x and mg is parallel to the x. And we can say here N and mg do not have contribution to the torque. I mean, N and mg will not help to rotate the block. In this case, we can say tau of N and tau of mg equal to 0. So L must be constant. And here we can say we have an isolated system. So L initial equals to L final. Okay? L before the collision, L initial. Before the collision, we have only a linear motion of the bullet. You know, in the case of a linear translational motion, we can write the angular momentum by R, M, and V. Okay, before the collision. R is the distance of the projection from the x to the velocity of the bullet. Here we have the velocity like this. and r is a projection from the x to the velocity, which is equal to L. Okay? Here the distance is L. So L times m times v before the collision. After the collision, here the system after the collision where the bullet will be inside the object, and here we have nothing after the collision. We get a rotational motion of radius L. So we have a pure rotation. We can put here I of the system times omega. Anyway, I need to calculate the angular momentum of the bullet block system. It means I need to calculate L initial and L final. This is L initial, which is equal to LmV, and L final equals to I times omega. We have a pure rotational motion. You know, here we can write I times omega, and you know here I of the system equals to I of the bullet plus I of the box times omega. Here the system will start to move with a velocity v. We can say here v final. I of the bullet, you know, as the final state, which is equal to 0 because we don't have ICM, because the X is not passing through the bullet, and also the X doesn't pass through the box. So we don't have ICM anyway for the box and for the bullet. We can say only we have m times L square plus 0 ICM of the box plus m L square. Okay? The distance between the center of mass of the bullet and the x-axis, and the center of mass of the box and the x-axis, and the axis, which is equal to L. Okay? We get finally m L square plus m L square times omega. This is L final. L initial equals to LmV, and L final equals to m plus m. We can take a common factor L square times omega. You know, we have a relation between V final and omega. Here we have omega between V and omega, where V final equals to L, the radius of the rotation, times omega. So omega equals to V final divided by L. So we can write m plus m times L square times V final divided by L. Okay, here we can eliminate L from here and square from here. We got finally like this. Now, what is the angular momentum of the bullet? It's okay. We calculated L initial and L final. B. Here, if you want, I can ask you to calculate V final. You can say V final equals to we can say L initial equals to L final if you want. Here, if I ask you to find V final, we can say L initial equals to L final. So L mv equals to m plus m times L times V final. So V final equals to, we can eliminate L and L. We get finally mv divided by m plus m. This is V final. Okay. Part B. What fraction of the original kinetic energy is lost in the collision? What I mean, fraction of kinetic energy lost. In general, you have to write like this, equals to the loss of kinetic energy equals to kinetic energy final initial minus kinetic energy final divided by kinetic energy initial. Okay, this is the fraction of kinetic energy lost. You know, initially we have only a translational kinetic energy. You can say here we have only m divided by 2 v square, v initial. At the final state, we have a pure translational, pure rotational motion. So we have I of the system divided by 2 omega square.